The world's oceans have evolved through geological time just as the biota has evolved on planet Earth. The oceans went from being these very hot and gaseous masses on planet Earth that had no oxygen to now these relatively cool and sometimes very cold masses of fluid that are full of oxygen, especially up at the surface. And they're very different from what some of the early ocean compositions were like. Now, what we've seen in the coevolution of life on Earth is that life has this way of adapting to whatever the environment provides to it, and then it can move forward from there and actually achieve capabilities via evolution that let them not only adapt well, but then control and change what that environment is composed of. We've seen that over and over again. One good example is the idea of photosynthetic bacteria actually flooding the early Earth with enough oxygen from their photosynthetic activity to oxygenate the planet by about 2.5 billion years before present. The Cretaceous is another dramatic example of biota rising to control and change fundamentally how the planet's oceans operate and what they're composed of. So in this Cretaceous time period, going from about 142 to 65 million years before present, we see that the world's oceans experience a proliferation or radiation of new kinds of very small single-cell organisms that lived in the water column. The first one is called a dinoflagellate, and the dinoflagellates are actually a type of plant-like algae that is capable of photosynthesizing. They're on the scale of about 1 millimeter in diameter. Some of them are smaller than that. And they're composed of a chitinous, almost cellulosic outer encapsulating shell in which they live, as we can see from this diagram. The next class of organisms that evolved in the oceans of the Cretaceous that fundamentally changed it were the diatoms. And diatoms are also photosynthetic algae-like organisms, but they live within a silicon dioxide, a quartz, or a glass skeleton. And as you can see from these diagrams, they've been called the small pillboxes because they do look like an ornate a glass box in which people, especially in Victorian England, used to store pills. Both of these organisms, the dinoflagellates and the diatoms, are incredibly important because of the fact that they photosynthesize. They're in extremely large abundances within the water column of the oceans. And then also because of how they create their skeletons, they absorb nutrients during the photosynthetic process. They create these skeletons, and it fundamentally has changed the relative mass distribution of nutrients like silica in the world's water columns. The third category that came up in the Cretaceous that again has fundamentally affected the planet are the coccolithophorids. And all of us who have ever used chalk, which is most of us, originally chalk that was mined from chalk quarries, especially those in England. The White Cliffs of Dover are another example. These are chalk deposits that are made out of calcium carbonate, and they're virtually 100% the skeletons of the coccolithophorids. And another way to describe these are calcareous nanoplankton. Calcareous means that it's calcium carbonate, and nanoplankton means that they're very small organisms that float in the water column. So as you can see from this diagram, it almost looks like a very intricate baseball that instead of having seams around it, it actually has individual plates of calcium carbonate. And so once these started proliferating and growing in the Cretaceous, again, it fundamentally changed some of the dynamics of the distribution of different organics, different nutrients, and the sequestration of CO2 into the ocean, because the formation of calcium carbonate skeletons at this kind of massive scale will change the amount of calcium carbonate and CO2 that can be incorporated into seawater. Now, there's one last group that did very well in the Cretaceous, and these are important to us because, again, they're on the scale of about 1 millimeter, but they're very useful because of the fact that they're very abundant in the Cretaceous and they are very distinct, and they change through geological time. So they provide us with a marker or a biostratigraphic indicator of geological ages. And they're called foraminifera. And as you can see from this, this image, the forams have, it's almost like a grouping of small baseballs that are put together, and then they have holes in the outer shell or the test of the organism. And from those, they stream what we call protoplasm. That is the materials that are inside the shell, inside the cell of the organism, and they stream it out into the water column. And as you can see from this image with a light behind it, those streaming protoplasmic masses allow them to derive organic matter from the water in which they're floating. And so these foraminifera, the calcareous foraminifera, they thrived in the water column, but also in the Cretaceous. And earlier in geological time, we had the proliferation of foraminifera that lived on the seafloor. And when organisms live on the seafloor, we call that benthic. So the benthic and planktonic foraminifera, coupled with the coccolithophorids, the diatoms, and the dinoflagellates, they were all very important new additions to the oceans of the Cretaceous. And it ended up doing what we call modernize the world's oceans. As we can see from this kind of map of the modern day seafloor, which is derived from multiple countries having these very extensive ocean drilling programs where they go out into the deep oceans throughout the world and for the last several decades have been taking cores. And from the cores in the deepest and the shallowest parts of the ocean, we've seen the remains of these organisms which all radiated in the Cretaceous very, very well preserved. And from the chemistries of their skeletons, we're able to reconstruct what ancient climate was like at a very high resolution throughout the Mesozoic and into the Cenozoic time periods. As we can see from this map of the world's oceans, again derived from these deep ocean drilling programs, we have a very distinct distribution of types of sediments. In some places we have the coccolithophorids dominating, and the calcium carbonate forms in the sea, in the water column, and it drops down to the bottom of the sea. In other places, we have no coccolithophorids. We have only the silicon dioxide diatoms. And those are prolific in places, especially where there's a lot of nutrients coming from upwelling of the ocean currents, but also where the temperatures drop. And when the temperature of the ocean drops too far, calcium carbonate dissolves. And so places where that dissolving takes place, then it's dominated by these silicon dioxide diatoms. So there are these very, very distinct distributions of ocean sediments around the world, and that's what helps us do the reconstruction of ancient oceans that we call paleoceanography. And from this image that we see from, again, one of the deep sea drilling coring projects, that there are also parts of the ocean that are 100% foraminifera. The single-celled, 1 millimeter diameter calcium carbonate organisms that stream protoplasm out from the holes in their outer skeleton. And as a result of this modernization of the ocean, then things like the concentration and the ratios of different elements in the seawater combined with the isotopic composition of the seawater has allowed us to have a very detailed record of oceanography and climate change throughout the Cenozoic. And these ancient records of climate change are very important to calibrate the future predictions of climate change on planet Earth. So the modernization of the oceans took place in this very crucial Cretaceous time period.